Alright, so last week we kind of continued talking about compounds and molecules, and we went through some of their physical properties, like, how many grams does a mole of something weigh, things like that. And so this week we're going to take our molecules now. We've kind of gone through all the details of an individual compound, and we're going to talk about what happens when we put them together and we have chemical reactions take place. And so we can't talk about chemical reactions without talking about chemical equations, because this is how we represent a reaction on paper. So you in the lab, you have your chemicals, you have your glassware and everything, and you perform a reaction, you see it happen, you make observations. And how do we write that down on paper? Well, we use chemical equations. And so these are just used to represent chemical reactions on paper. And so it's a shorthand, and this is actually going to be a tool that we can use later on in the videos this week. We'll actually be able to use it for calculations and things like that. But to start out, just kind of what does the format of these, what do these look like in terms of format? What are all the pieces? What does all the information, mean? Where is it presented? That's what we're going to talk about first. And so, for example, I'm going to describe a chemical reaction, and then I'm going to write the chemical equation for it. And you'll see that the chemical equation is much faster to write than actually physically writing out all of the stuff in the reaction. And this is a simple reaction too, and it still beats it. Alright, so hydrogen gas and oxygen gas will react to form water vapor. So hydrogen gas is combustible. And so let's look at what this looks like as a chemical equation. So that's a short sentence. It's not too bad. Some reactions get much longer. It could be like a paragraph to describe it. But they all end up being one line in terms of a chemical equation. And so here's what we're saying. We have two of these hydrogen molecules. They're going to react with one of these oxygen molecules. And I'm going to get two waters out of it. That is my chemical equation, all right? And so let's kind of break down the pieces here. So on the left, we have what are called reactants, and on the right are products. And you might only have like one product or one reactant, but you have a product side and a reactant side. And so there's the stuff you start with, a reaction happens, and then there's the stuff you end with. You produce products, you react reactants to make them. And this little arrow in the middle here, as creative as ever with our naming, this is known as the reaction arrow. So this arrow represents the reaction happening. So we read it just like we do, a sentence. We go left to right. We start here and we end here, and what happens in the middle? The reaction happens. So we can lay out, maybe 20 reactants, however many we need to put there. Then the reaction happens, we get however many products there are. So this is what separates them. It's kind of like the equal sign in a math equation. Alright, so what else is there? Well, there's these little letters here, in parentheses at the end. And that represents our phase of matter. And so in this case, everything is a gas. I'm reacting hydrogen gas, I'm reacting oxygen gas, and I'm making gaseous water. Or water vapor. So, this can be important to know, like if you're trying to reproduce a reaction. Do I need something that's solid? Do I need it dissolved in water? Do I need to make sure it's melted as a liquid? Do I need to make sure it's a gas to do a reaction? We put that information in here. Alright, and so a G is for something in the gas phase. An L is something in the liquid phase. S is for solids. And there's one more that's very popular, and that's AQ. And this is aqueous, which means dissolved in water. We do a lot of reactions with stuff dissolved in water. And we'll talk about one of those types of reactions later this week. And so every species has this phase of matter, and they all have their chemical formulas. Alright, and so what is happening here is, these molecules come in contact and they rearrange into a new molecular product. And then the last piece are these numbers out front. And so I'm saying there's 2 hydrogens in this reaction. It makes 2 waters. We call this our stoichiometric coefficient. If there is no number shown, that just means there's 1. So there's 1 oxygen molecule here. Because why would we write a 1 when we can imply it? What's easier? What involves less writing? Guess what the chemists are going to do. Okay, so this is an example. There's a little bit more information that we could present. This reaction didn't need it. But we can use a few more tools here to show some more information. If you see your reaction arrow with a Greek delta, also known as a triangle, over it, this means that heat has been added to help the reaction happen. And so, for example, we'd have something like calcium carbonate, which is a solid. If we heat it up, it will actually decompose into calcium oxide and CO2 gas. Okay. We can also put a catalyst over our reaction arrow. So for example, we could have a reaction like this. These are all in the gas phase, so CH2CH2 plus H2 is going to react, and the really good catalyst for this reaction is platinum metal. I'll explain what a catalyst is in a second, but then we just get our products, so CH3, CH3. So this is a little bit different way of writing compounds, but it's a good way to write these carbon-based organic ones. So basically we're just adding an H2 to a molecule. We're just adding 2 more hydrogens to it. And to do that we use platinum metal, which makes it a lot easier to get to happen. And so what this is the catalyst, because it's not a reactant, it's not a product. We don't use it up, we don't produce it at the end. So we just basically would take a chunk of platinum, put it into this gas mixture, and when we're done we just pull the platinum out and it's still just a chunk of platinum. So it just helps speed up the reaction, but it does not get used or produced. So it's separate from the reactants and products. And so because it's separate from the reactants and products, where we put it? Right over the arrow. Okay. So, the last thing is, if there's no reaction, then on the product side you can just put NR. So you have your reactants, and then they don't make anything new, so you don't want to just write all your reactants again, you just write NR for no reaction. And that's really all the tricks to these chemical equations to start out. So, we're going to talk about them some more in the next video. We're going to talk about what a balanced chemical equation is and how to make sure you're dealing with a balanced chemical equation. And if you're not, how to make it a balanced chemical equation. I will say this was a balanced chemical equation. But that's for the next video. So, hopefully you're comfortable with the format and the idea that what this is just, we do a chemical reaction, how do we write it on paper? So it's just like you write a math equation to show doing math operations on paper. It's just a shorthand for some process, right? Addition or subtraction, there's a formula, and same here, but just for chemical equations now. So matter interacting with other matter and rearranging to have a new bonded form. That's kind of, I think, where chemistry really starts to take off, because you're doing the chemical reactions. Alright, so we'll talk about balancing these next, and that'll probably be a little bit longer than this video, so just a heads up on that.